Okay, so some comments on the Gauss-Seidel scheme, which we just looked at in Excel. If the matrix, that's the matrix we were solving, right? You remember the matrix coefficient, the matrix of coefficients, which multiplies the pressure and is set equal to the right-hand side. So this is AX equals B, right? If this matrix is diagonally dominant, and I explained that before, it means that the value on the diagonal, the absolute value of what you have on the diagonal, if that is greater than the sum of the off-diagonal terms. So if the absolute value of this is greater than the absolute value of this, and the absolute value of this is greater than the absolute value of this, that's the sum of these two absolute values, right? And for every row, that is the case. So the absolute value on the diagonal is always greater than the sum of the two off-diagonal terms. Then that matrix is diagonally dominant. And that is all you need to get convergence. That's a sufficient condition, but it's not necessary in order to get convergence. What that means is you can actually get convergence sometimes even when it is not diagonally dominant. But if it is diagonally dominant, you will converge on the correct answer, regardless of the initial value. Now, the initial value can affect the rate at which you will converge, and that's what this point is. You will converge regardless of the initial value, but how fast you converge will depend on the value you provide as initial guess. There are methods to speed up convergence, and we'll talk about some of them, like over relaxation and all. Already we saw these, right? When you have your Gaussian elimination solution and the Gauss-Seidel schemes, this is direct method, this is iterative method. They both give about the same answer, provided you run the Gauss-Seidel scheme long enough, right? But for the Gauss elimination method, you will always converge on the correct answer once you follow through the LU factorization method and backward substitution method, which we discussed on that. So, problem for you to practice. I already explained how to set up the Gauss-Seidel scheme in Excel, right? So now we can get to use it. And I will like to make it clear that this iterative approach is actually very important. It's not limited to reservoir simulation, right? This is how you will solve any system of equations. So you will see this in geomechanics, you will see this in fluid mechanics, in CFD simulations. I mean, anytime you have to solve a system of equations, now you have two ways to solve it. If the system of equations is very big, you use the Gauss-Seidel. If it's small, you use the Gaussian elimination method. And to clarify, in exams, quizzes, and all, I won't require you to work out this iterative scheme, for instance, by hand for all of the number of iterations, right? But that doesn't mean I can't test you on it. So what I mean is I can actually give you maybe one step and just have you calculate one or two values. So you still need to understand the process so that if you see any question on it, you can solve it. The question will not test your speed, right? It's just going to test your understanding. So it's going to be a very simple question that once you understand the iterative process, you will be able to solve it easily. So don't just ignore it and figure out, oh, this is too much to be asked in an exam, so I'll just learn how to solve the system with my calculator. No, you need to understand how it works so that if I give you like a calculation that requires you to say calculate P3 in the Gauss-Seidel scheme, given P2 at the current iteration and P4 at the previous iteration, you know exactly how to do that. So understanding is required. Good. So to practice, remember we had set up the problem for 10 days. Can you solve it for 20 days using both methods, the Gaussian elimination and the Gauss-Seidel? And of course, just do the Gauss-Seidel in Excel. And I want you to solve it in two ways. You can start with, this is method 1. Start out with the solution we just got, right? After say 33 iterations when it had converged. Start out with that. And then move another delta t of 10 days. So what that means is the initial condition now is no more, the starting point is no more the initial condition. The starting point is whatever we just got in the previous video, right? So that's the starting point. Then you increment another delta t. So even though delta t is 10 days, the solution you're solving for is after 20 days because there was 10 days from initial conditions. We started out at 0. Then we calculated 10 days in the previous slide. And now I'm asking you to calculate 20 days. So between this and that is 10 days. So the pressure solutions are going to start out using the value we got here in this first bullet. In the second bullet, you know what? Start out at t equals 0 and jump to 20 days. So delta t is what? So delta t is 20 days. And you just repeat the calculations we did before using the two methods, Gaussian elimination, Gauss-Seidel. And just to put it in perspective, I'm going to open up the slide for module 2. So this is where the equation was, right? Remember, this was the continuous form, which we discretized, and it gave us this, right? Using finite differences on these two terms. And we had said this is D, right? And so all you need to calculate is to provide these values which were given. And that we did here, right? So these are the input parameters. And then this is the equation for D. Substitute each of those values. And keep in mind, this is delta t, right? We use 10 days. The equation is set up to be for time to be in hours, right? That's what this conversion factor does. So this is 24 hours in a day times 10. That's where you got 240 from. And you got this as your D, which you used in all of the equations, right? All of this D is that value you calculated using delta t of 10 days. And you started out with initial conditions. So now in the second process I had shown, well, just put delta t equals 20 days. So what's 20 days? It's 20 times 24. So this will become 480 and this will become half of that. Then you will use all of that in these equations for D. In place of this, you'll be using half of that. So this will probably be half of this, right? This will be half of that, which is 168. And then solve the equations afresh. So this will be half of that. This will also change. These coefficients will change. And that's method 2. Method 1, we use the same delta t, but the pressures will start from the solutions we got in the solution process for Gauss-Seidel and Gauss elimination methods. Good. So we move back to module 3E. And then in the next video, we'll talk about how to calculate rates from the pressure solutions we already have.